Hi, let me show you an application of explicit MPC in the domain of power electronics. Power electronic systems can be found in many places. They can be found in your cell phone and laptop battery chargers. They can be found in the metros and trains we hop on every day, and even in modern power stations. We were studying one particular DC-DC topology called the buck converter. The buck converter has at its input a fixed DC source, say 15 volts. Its purpose is to send energy to supply a load at a lower voltage, say 5 volts. It does that by switching on and off this transistor really fast. And if you regulate the amount of time it stays on versus the amount of time it stays off, you can control the flow of energy from the primary, from the source, all the way down to the load. The remaining components are here to make this electronic circuit work, but also to filter out some of the ripple that will show up here due to this high frequency switching activity. Very well. All of this is usually done in closed loop. And if you need to close a loop, you'll probably use some form of a computing device, illustrated by this microcontroller. Of course, you could have something else in its place. For example, a dedicated, specialized analog circuit, which is really common in the field, or even an FPGA. But we'll focus our attention on microcontrollers. This computing platform has to measure both states of this dynamical system. The current flowing through this inductor and the output voltage. It then samples these values and executes an appropriate control algorithm to calculate an input that is then applied to the plant. This input will look something like this. It will be a PWM signal. PWM stands for pulse width modulation. For example, if the microcontroller decides that the control input should be 0.25, then the PWM signal will stay at a high level for 25% of the time and at a low level for 75% of the time, and so on. So this signal is bounded between 0 and 1. Finally, one last technical detail is before actually hitting the gate of this transistor, this electronic signal has to pass through something called a gate driver that boosts its current capabilities in order to drive the gate of this transistor. Very well. So that's the operating principle of a buck converter. We actually built one of these in our lab. This was a collaboration with a semester project student called Martin back in 2020. The first step was to select the components, choose their values. Then we used the Autodesk Eagle software to both draw the schematic diagram of the circuit, specifying all the interconnections, and also to design the actual PCB, the printed circuit board that would then implement our buck converter, shown here on the right. An actual photo of the prototype that we built can be seen on this slide. Yes, it looks a little bit more complicated than the simplified schematic that I've shown you earlier. But let's try to identify the main components of the board. First and foremost, the input DC source. It is connected here to this wire-to-board connector. We have our switch, that in this case is a MOSFET, or large bulk inductor, or two output capacitors associated in parallel, a diode, and finally our loads. From a control perspective, we also have the place where we connect our input signals, the PWM signal. So the PWM goes here, and here goes its ground, its reference. And on these headers, the microcontroller has access to the feedback signals that are generated by two sensors. A voltage sensor that in this case is a simple voltage divider used to scale down the voltage to levels that are more microcontroller friendly. And also a current sensor. that measures the current flowing through this trace indirectly. It actually measures the voltage drop across this very small and precise resistor. So that's essentially it. So we built this PCB, we soldered all the components, and we also tested it to make sure it was working properly. After that, we decided to derive a mathematical model for it. We did not only want to model the rough behavior of the system, but also we wanted to capture the damping and the energy losses associated with each component. This is why you see so many resistors all over the topology. There's a resistor associated with the MOSFET, one with the inductor, one with the capacitor, and we have even included the forward voltage drop across our diode. Brief recap, we have two states. One of them is the inductor current, and the second one is the output voltage. We have one control variable, the duty cycle, the time that PWM signal stays high. Okay, so there's actually a very classical and widespread approach to deriving models for switched mode power supplies, such as this one. It's called the averaging technique, and it dates back to the 80s. Now, if you use the averaging technique along with some basic circuit analysis, what you get is these two ODEs. One for the inductor current and one for the output voltage. These are not linear though, because the states and the input, they multiply each other here and there. You see it? Now, we need linear models, a linear model, because we want to apply linear MPC here. So what did we do? We linearized these dynamics around an equilibrium point. Now, how do you find the equilibrium point of this system? You have to, for example, we knew that we wanted the output to be at 5 volts. So that's the desired equilibrium for X2. And then in order to figure out what X1 and U are, you simply set these two equations to 0 and solve for X1 and U. So the equilibrium value for the inductor current is nothing but the output voltage divided by the load resistance, which is not really surprising if you are an electrical engineer, right? Very well. So then you linearize these two equations around these points, and you get a continuous time linear state space model, AX plus BU, whose matrices A and B, of course, will depend on the parameters of your particular converter. As a last step, we had to discretize these dynamics, so we used the zero-order hold method available in MATLAB. Controller design phase, a very standard tracking MPC formulation with a quadratic cost with both terminal ingredients, the terminal cost and the terminal set constraint. By the way, this here was the maximal invariant set associated with the LQR policy. And box constraints for the states and the input. The parameters can be seen here on the right. Our prediction horizon was 10. Here are our weights. And let me draw your attention to the following constraint. We needed the inductor current to be within 0 and 200 milliamps. You'll see in a moment why. All right, so we designed our MPC controller and we tested it in MATLAB in simulations, and it worked just fine. Now the question is, how do you actually deploy it? How do you do all of this in practice? Especially if what you have at hand is a teeny tiny microcontroller that runs at 80 megahertz. It only has 128 kilobytes of RAM and 1 megabyte of flash memory. This was, by the way, the STM32L476. You can read its datasheet online if you wish. And furthermore, you have to do all of this at a rate of 10 kilohertz. So sounds quite challenging, doesn't it? So there are two options here. Number one, you pick a very efficient and lightweight embedded solver to try and solve this QP at this rate with this hardware. Number two, you can try to deal with all this complexity offline, and online simply perform very trivial computations, where you go through a lookup table and then you decide which one of the control feedback gains you will use at a certain point in time. So that's exactly explicit MPC. And if you think about what we have here, or scenario, we only have two states and one control variable. So overall, not many variables, right? Kind of makes sense to see if MPC could, explicit MPC could be a good fit for this problem. This is exactly what we did. We used the multiparametric toolbox, MPT, to calculate the explicit MPC controller. But once we did that, we realized that the solution was simply too complicated still. It had too many regions. And the apparently simple task of finding in which region you were at every point in time and then extract the feedback gains was already too much for the microcontroller to handle. This is when our very special controller simplification technique comes into the picture. It is based on a tailor-made neural network that has as its nonlinear layer, as its nonlinearity, a parametric QP. So it has an optimization problem inside of it. Why is that? In order to match the format of an MPC controller, which is nothing but a QP itself. So they match each other. How is this neural net trained? It's trained based on a data set that can be gathered either from the original QP, so you can either solve the QP, or you can directly sample the PWA function, the explicit MPC controller. It's the same. So it's made of use, access, and use. So how do you gather this data? You select a point, and then you record the coordinates, the states, and solve the MPC problem there in order to get the corresponding U value. And then you also store that. You repeat this over and over again, and that's how you compose this data set. These X and U pairs are then used to train the neural net and adjust all of its internal parameters through backpropagation. And if you do that, what you get, what's interesting about this specific neural net is that after it's trained, it can be also converted into a piecewise affine format. So it becomes a piecewise affine map itself. So you see, there's a correspondence here. But this PWA function is potentially way, way simpler than the original MPC controller. Okay? All right, so let's try to wrap our heads around what's going on here. This is not a standard learning problem. Usually what you have is data, and you're trying to learn the underlying unknown function. But in this case, you already have the function. You know exactly what it is, and you can compute it explicitly. You can even write it down. The thing is that you're using data coming from this function to learn a simplified representation of it in the hopes that one exists and that it's not very far away from the original one. Okay? If you're interested in this work, you can read more about it in our paper. That's, by the way, freely available online. The results that we got were actually very surprising. On the left, you see the original explicit MPC controller partition of the state space. It's quite complicated. It has 153 regions, and some of them are even really, really small, which could be complicated for our microcontroller to even represent. By the way, it only has 32 bits. On the right-hand side, we see the simplified version of it after we used our neural networks. And it's way, way, way simpler. It only has 6, actually kind of 5 regions because one is really tiny. And this could be easily implemented and deployed on our microcontroller. So overall, an excellent simplification results. Now the question is, okay, so the partition was simplified, but how about the actual control surface. Was the duty cycle resulting from this feedback law similar to this one? In other words, what about the third axis? The original surface is on the left with all its 153 regions that are all divided here in its domain. And the learned surface is shown on the right. Actually, this is the surface evolution across different epochs of our neural network training process. And as you can see, it struggles at the beginning, but then towards the end, it figures out what to do. And it resembles a lot the original surface. The final results can be seen here. And well, it's pretty clear that the two match very well. They are virtually indistinguishable, except for this small portion where you can see some differences. Nevertheless, the experimental results were good under this simplified controller, as I'll show you in a moment. Before I show you the experimental results, let me say a few words on embedded deployment, more specifically on what goes on inside a microcontroller. An MCU is very similar to a standard processor that you can buy at Digitech. It has a core inside of it where it does its math, and with some registers, an arithmetic and logic unit, a floating point unit, and stuff like that. And it also has some memory, okay, to store your program, the actual instructions, and perhaps some data as well. Now, what distinguishes MCUs, microcontrollers, from regular processors is that MCUs have more stuff inside of it. They have analog to digital converters, they have timers, they have PWM blocks, etc. Everything that is not the main processor core nor the memory we call a peripheral. So the ADC is a peripheral, the timer is a peripheral, etc. Now, these peripherals are important because they interface the MCU with the external world. For example, the ADC, if it samples the output voltage of our buck converter, it will then store a digital value inside one of its registers, and then the processor core can go there and fetch that information to do some math with it, for example, to execute the control loop. So each peripheral has a set of configuration registers and data registers that the processor core will write to and will read information from. So that's the general architecture of a microcontroller. The mental picture that you could have is the following one. The processor core is the boss, and it assigns tasks to each one of its subordinates, the peripherals. Since each peripheral is a different piece of hardware, they can work on their own without necessarily interrupting the boss. Now, here are the internals of an MCU. For example, this could very well be the PWM block responsible for generating that signal, the input signal to be applied to the plant. And the PWM block has a pad where there's a wire connecting it to really one of the pins of this integrated circuit. So that's how the code you write can influence the external world. Regarding the embedded firmware, it's usually based on the principle of reactivity. There's always an initialization phase where you initialize each of your peripherals, the peripherals you need. Next, the processor core simply sits there and waits. It's not uncommon to see empty while true loops. What is it waiting for? Well, it waits for either internal or external signals, events. Maybe someone has just pushed a button, or maybe you have a timer who has finished counting. In both cases, these events, these interruptions, they raise a flag. The processor core then responds to that event by executing an appropriate piece of code, what we call the interrupt service routine, ISR. So for every single possible interruption, you can write down one ISR. The processor core, once it finishes executing that piece of code, it will simply go back to waiting. And then the cycle repeats. In our particular application, what did we have? Well, in the initialization phase, we had to initialize one timer to count up to 100 microseconds. Remember, our sampling frequency was 10 kilohertz. We had to initialize two ADCs, one for the output voltage and one for the inductor current. And of course, we also had a PWM block to generate the PWM signal that would then be applied to the plant. Inside the timer ISR, we wrote our MPC algorithm. First, we had to sample the two analog signals and scale them. Next, we solved the point location problem, so figuring out in which of the regions you are to extract the right feedback gains and compute the associated U. And finally, last step was to take this U value and send it to the right PWM block, to the PWM peripheral, so that the duty cycle of the PWM signal would be updated. Okay, so that's the general picture of our embedded firmware. A cool picture of our workbench. We've got our buck converter, our input source supplying 15 volts to it, and our microcontroller, and some of the lines of our embedded firmware written in C. Down here, some advanced comments on how we've managed to speed up the code. In reality, we configured a DMA block to automatically transfer the ADC readings to the main memory. So this was not done by our main processor core. We had to average 8 samples to get rid of some noise. We did not use any floating point variables. And finally, we have used a very simple open loop state estimator to correct a certain problem. That's a very subtle one associated with the diode barrier. Now let's talk results. What you see on your screen is the open loop response of this dynamical system. It looks pretty bad. Even though you want to settle down at 5 volts, the voltage waveform peaks at 8. The current is even worse. Look at the size of this hill when compared to the final steady state value. That's an overshoot of over 700%. Can you now improve this transient response using MPC? Yes, that's very much possible. This is what you see on your screen. The voltage waveform goes up and it's even monotonic, so there's no overshoot. It converges faster to the steady state value. The current rises and then it hits the constraint. So it's 100 milliamp per division, and that's 2 divisions. So it hits the constraints that we had defined, 200 milliamps. And then it goes down to the steady state value. So overall, this looks much, much better than the open loop response. Just for the record, a smooth startup could be also achieved with a very simple hand-tuned PI controller. That would take maybe 5 hours to code, a very simple one. However, a PI controller would be very much slower when compared to MPC. It would be 20-50 times slower. MPC shines because it can go fast and respect the constraints. This is its strength. In blue, I'm showing you the time it takes for the MCU to execute the timer interrupt service routine. In other words, the explicit MPC controller code. Let's zoom in. We're now at a scale of 100 microseconds per division. So this is 100 microseconds, exactly our sampling period. And the MCU is taking only 27.32 microseconds to execute, to go through all our regions and then to extract the right feedback gain and to apply that to the system. So only less than 28% of the available time, which is good because this also means there is some time left for it to execute other tasks if needed. For example, communication with an external device. All right, so this was pretty much everything I wanted to share with you. Thank you so much for your attention.